Now, with the things already discussed, like universal elimination, existential elimination, and existential introduction, let's try to solve this problem. Now, while we'll be discussing this problem, we will get to learn some new things and we will be using some things that we have already learned. So, if a perfect square is divisible by prime p, then it's also divisible by square of p. Every perfect square is divisible by some prime. 36 is a perfect square, and this is the thing we need to prove. Does there exist a prime q such that square of q divides 36? Now we have here this problem, and we will divide it into three uh, statements. One is if a perfect square is divisible by a prime p, then it's also divisible by square of p. Every perfect square is divisible by some prime. It will be second statement. This will be first statement. And 36 is a perfect square. It's going to be a third statement. And this is what we need to prove, which is does there exist a prime q such that square of q divides 36? Now, here what we observe is there are things like if and then, which means that there is going to be an implication. So this is first thing that we infer from this. Second is that there is a perfect square. So x is a perfect square. Then third thing that we see is uh, divisible. So it means they have to be two different kinds of entities. Uh, then we have a prime. So y is a prime number, and 4 is x is divisible by y, or perfect square is divisible by prime. Now we have to understand something new here. If we were to divide a simple number a is divisible by b, we will represent it with like this: divisible a comma b. But we are talking here about two different things, which is x and y, and these in themselves are represented with a predicate logic representation. So uh, we could represent it like this. So we are going to represent this statement, which is perfect square is divisible by prime by something like this: divisible perfect square x comma prime y. Now this can also be represented in another form, which is that we will take these out, perfect square will be out, prime will be out, and they will be all ended with divisible x comma y. So here goes the representation: perfect square x and prime y and divisible x comma y. So these two are one and the same thing. But what here is given is that if a perfect square is divisible by prime p, then it's also divisible by square of p. So we have another thing here, which is square of p. So for prime p we used y, so here also we are going to use y. Now let's try to write this complete statement. If a perfect square is divisible by a prime p, then it's also divisible by a square of p. Every perfect square is divisible by some prime p. So it means that something, if a perfect square is divisible by prime y, then it's also divisible by the square of y. So I can represent it either with this thing or this thing. but I will choose this one. Let's write it here. Perfect square x and prime y and divisible x comma y. So the statement says if this is true, then divisible x comma square x comma square y. This is y here is true. But we are talking about all the numbers. So outside this, we are going to have a universal quantifier, which is x comma y. So this is our first statement. Then a second statement says that every perfect square is divisible by some prime, which means that every perfect square is divisible by some prime. So we have things like every, it means we're going to have a universal quantifier. Then some, we're going to have an existential quantifier. So perfect square is represented with x and prime is represented with y. So let's represent it like this. For all x, for some y, because for x is representation of perfect square and every, it's about every x, therefore we're going to have for all x, and here for some prime, therefore we are going to use existential y. There exists at least one y, and it goes like perfect square is divisible by some prime. So again we're going to have perfect square x and prime y and divisible x comma y. So this is our second statement. Now the third thing that is given is 36 is a perfect square. 4 is 36 is a perfect square. And the thing that we have to prove is that there exists a prime q such that square of q divides 36. So how will we represent this? So let's write it beforehand because it will be easy for us to then conclude this thing. So this is what we have to prove. There exists a prime q such that square of q divides 36. So there exists is represented with this statement, this quantifier. There exists a prime q, and we have represented prime with y. So we are going to have y here. And it's going to be prime, there exists prime y such that we know with existential we are going to have an AND operator. 36 is divisible by square of y. So this is what we have to prove. Now the first thing that we will do is using, this is third and this is what we have to prove. Using third and second, we can have a universal elimination because 36 is a perfect square, and here we have a variable x, and for variable x we are having a universal quantifier. Therefore, this statement could be written as like this. Let me shift the new screen. So this statement becomes perfect square 36. Here we're still going to have y because the only thing that got removed was a universal quantifier. Perfect square 36 and prime y and divisible x comma y. Here we are going to have 36 comma y. Okay. Now we're also given, so let's put it here as 4. Now we're also given that perfect square is divisible prime p. So p can act as a Skolem constant. And we know by using Skolem constant there has to be this existential elimination. So this statement becomes perfect square 36 and prime p and divisible 36 comma p. So we are having two constants, 36 and p, and by introducing p or by substituting p for y, we eliminated this existential quantifier. So that's why in this statement you are not able to see any kind of existential quantifier. Now with this in hand, what we find is that it is similar to the left portion of statement 1, and this is for all x and y. So here for x and y we have 36 and p. Therefore uh, from the first statement and fifth statement what we find is that this left hand side when this statement is compared with the left hand side of this, it gives us divisible x square y. So we are going to have here divisible 36 comma square p. So this is 36, and from 5 statement 5 and 6, what we find what do we find from the statement 5 and 6 if we compare this and this? The thing that we obtain is prime p and divisible 36 comma square p. So it's all about constants. As we saw in the previous case, if we have no knowledge and then we are provided with some information uh, and we update that in our knowledge base or database. For example, in this case we see 36 and p. It's a particular case, and now we updated it. So now we can introduce the existential quantifier. So uh, we will introduce in 7 the existential introduction, and this statement becomes for some y prime y and divisible 36 comma square y. So basically this is what we had to prove, and we found it. Here we had to prove this for some y prime y divisible 36 square y. So this is what we find here.